To host the 2026 FIFA World Cup in Texas, engineers solved a massive spatial problem, enclosing an interior void of 3 million cubic meters. Achieving a continuous span of this magnitude required engineers to abandon standard architectural framing and conventional vertical supports. The structure had to satisfy 3 compounding constraints simultaneously: maintaining a completely column-free span, supporting immense dynamic roof payloads, and regulating a biological microclimate against extreme external temperatures. To survive these overlapping forces, engineers relied on extreme structural statics, applied 19th century locomotive mechanisms, and heavy-duty thermodynamic stratification. Analyzing AT&T Stadium from first principles reveals a highly precise, integrated megamachine. The primary architectural barrier in stadium design is that internal pillars obstruct audience sightlines. Eliminating them mandated the use of 2 1,400-foot continuous parabolic arches to span the entire structure. These arches face an extreme payload constraint. They must simultaneously bear a 1,500-ton dynamic roof system and hold a centrally suspended 600,000-kilogram LED screen array. The internal geometry to support this weight was established in 1875, when Gustave Eiffel designed bridges across Portugal's Douro River without using vertical pillars. Isolating Eiffel's triangular steel truss matrix, we see that because a triangle maintains its shape under extreme pressure, the downward compressive load is distributed without deformation. This payload is then transferred outward and anchored into 4 massive peripheral concrete abutments. Anchoring heavy steel in Texas introduces an environmental vulnerability. Steel expands drastically in extreme heat, generating enough shear force to fracture the concrete abutments. To prevent structural failure, engineers integrated specialized thermal expansion joints between the steel and the concrete. These joints physically decouple the materials, allowing the stadium to expand and contract. Resolving this static load prevents the arches from collapsing, but it only serves as the rigid foundation to support the massive mechanical forces positioned above. The actuation challenge involved safely moving 1,500-ton retractable roof panels upward along the 30-degree curved incline of the primary arches. The intuitive solution utilizes modern, heavy-duty industrial tensile winches and steel cables to pull the weight. A tensile approach introduces massive weight penalties. A cable system capable of lifting this load would add 3,000 tons of winch and counterweight capacity to the primary arches. This model illustrates the mechanical failure risk of kinematic asymmetry. Even a millisecond of desynchronization between spooling cables causes the massive panels to twist out of alignment. This twisting induces lateral torque across the primary truss, generating uneven stress that threatens structural collapse. Furthermore, if a single steel winch wire snapped under tension, the uncontrolled free fall of the panels would act as a massive wrecking ball. Tensile systems are too chaotic for this payload. Mechanical stability on this scale demands a rigid, bidirectional locking mechanism. Engineers turned to a 150-year-old mechanism invented by Sylvester Marsh in 1869 to push locomotives up steep mountains without slipping. The system utilizes a rigid, toothed track embedded in the structure, paired with meshed geared wheels attached to the load. At AT&T Stadium, 130 individual 7.5 horsepower motors provide synchronized power directly to these geared wheels, or pinions. Because the gears are physically meshed into the track, they naturally lock bidirectionally, acting as absolute brakes against gravity. This exact same gear logic is scaled vertically to actuate the stadium's 12-story high glass sliding doors, which weigh 86,000 kilograms each. By utilizing 19th century locomotive kinematics, engineers guaranteed perfectly symmetrical, synchronized load distribution during every actuation cycle. The final hurdle was cooling a sealed interior volume equivalent to 3 Burj Khalifas against the aggressive external Texas climate. The solution relies on an 11,000 refrigeration-ton chiller system pumping air through upper ducts spanning 6 feet in diameter. This models thermodynamic stratification. Because dense cold air is heavier, it is injected from high ducts to cascade downward, washing over the stands and playing field. As the air warms, it becomes lighter, naturally rising into the upper vault to be recycled. This precise climate control must also accommodate FIFA's strict requirement for a living, natural grass pitch. Supporting organic life on a concrete floor required elevating the field level 6 inches for drainage matrices and installing artificial UV arrays to supplement sunlight. Because the dome cannot sustain grass, the turf is cultivated in Colorado, transported in refrigerated modular trucks, and installed precisely before the tournament. The structure functions as a carefully calibrated life support system, manipulating internal fluid dynamics to sustain a temporary biome on demand. These distinct subsystems rely on one another. Eiffel's trusses bear the load, allowing Marsh's gears to actuate the roof, which seals the environment so the thermodynamic chillers can sustain the biological turf. Millions of pounds of steel, glass, and atmospheric pressure are manipulated simultaneously, cycling through continuous mechanical stress without structural fatigue. Meeting global event demands requires erasing boundaries between traditional architecture, mechanical physics, and industrial logistics. The stadium functions as a finely tuned mechanical assembly, actively modulating its own mass and atmosphere to meet the requirements of the world stage.